Hi, everybody. I'll present you to do some results about my first years in thesis about influence of laser parameters on the melt-pool morphology for laser powder bed fusion during keyhole regime. So first, yes. What is laser powder bed fusion? So laser powder bed fusion is most commonly used process for metallic additive manufacturing. So you have a machine here. So it's a LPBF machine, and I use at Ennis a Pro X 200. So in this process, you have here a storage of powder, and here you have the build platform. So during the process, a recoater put a thin layer of bed powder on the build plates, and there a laser come to melt really locally the powder to build your pieces in 3 dimension. So at each layer, the build platform go down and the powder platform go up, and a new thin powder bed can be made by the recoater. And for my thesis, I'm looking for the interaction here between laser and powder and previous melted layer. So in my case, I'm working in the specific regime, which is the keyhole regime. So I will explain what is it now. So first, you have the laser will hit the surface, and the laser absorbs the energy of the laser and creates a melt pool here near the laser near the laser beam. Because the temperature is hotter near the laser beam than on the boundary of the melting pool, you created a gradient temperature, and it created a surface tension gradient. And it's created here convection inside the melting pool, which is morphology convection. In this case, we are in the conduction mode, which is a stable way to build to process. But I work with the keyhole regime, so for this one, you need to put more energy by modify the power of the laser, the scanning speed, for example, and focusing your laser beam. And in this case, you can reach the boiling temperature of your melting pool, and metal vapor appear. And it's created a cavity. So this is the keyhole cavity, which is maintained by the evaporation of the material inside the melting pool, which is recall pressure. So maintain the keyhole open. Nevertheless, you have some hydraulic pressure and surface tension that try to close the keyhole cavity. So this regime is really unstable because you can really create a pore, and really big pore during the process. And now we are in the keyhole regime and also a convection regime. So basically, we have for all material for laser powder perfusion this kind of process window as function of scanning speed and power of the laser. So first, you have at low scanning speed and high power the keyhole regime, which can see that you are in deep penetration inside the material because of the formation of the cavity. On the contrary, with high scanning speed and low power, we have in a lack of fusion regime. It means that you don't have enough energy to melt the melt pool, to melt the powder bed, and to create a good single tract. And you have also boiling effects with high scanning speed and high power. It's like you have some droplets on your material, and you don't have a continuous single tract. And at the middle of this, you have the stability windows where all is good. So now in my thesis, the project is to study the interaction between laser and matter and powder bed, and especially during the keyhole regime, to understand the dynamic evolution of the melting pool, because we see that in the keyhole regime, you go deeper in the material. And of course, if you go deeper in the material, you have a big instability, and you can create keyhole pore. And it's to understand the pore formation in order to avoid to create pore during the process, or on the contrary, to control the porosity inside the material. So here we come back on the process windows. So I say I work in the keyhole, and I am especially in this red area, where we are on the transition between stability regime and keyhole regime, because you have to know that pore formation, it appears when you really on the hard keyhole mode. So you can be on the keyhole mode without creating pore, and this is the purpose of the thesis. So now we'll talk about my methods, and after I will talk about the laser analysis that I made on the ProX 200 at ENIS, and after I will show you some results that the single tract I made, and I will talk about some perspective. So I use stainless steel powder. As I said before, I use additive manufacturing LPBF at ENIS at Saint-Etienne. And I fabricate a single tract like this. Yeah, just one path of the laser. And I change laser power, scanning speed, and also the distance between build plates and lens, which is the focal distance. So I have 3 values for each parameter. And we have to notice that -7 is the focal point of the laser in the condition that I use. And secondly, I made a laser analysis, so with a focus beam profiler from Synology. So this is the environment of the ProX 200, and we put this little box just under the laser in order to have an image of the spots as function of the time. And here, the laser of the machine is just here, and we can, and it's composed of the optical fiber, collimator, SCAD-HEM, and F-theta lens. And also we have, I don't mark it here, but we have here, between the F-theta lens and the build plate, we have a window to protect the F-theta lens from the environment of the chamber. So this focus profiler of Synology is really interesting because you can work with beam stability and to see the evolution of the time as function of the time of the spots So this is what I made, and of course I made some caustic at 115 watts and 200 watts at cold, hot start of the layer and hot end of the layer machine condition, and I will explain what is it now. So here it's beam stability, so you can see here the evolution of the spot size as function of the time. So in the x-axis you have the time, and y-axis you have the spot size. And we can see that during the time you have a big evolution of your laser spots, which can be really problematic for your fabrication, of course. So at the beginning, when the machine is cold and is the really beginning of the fabrication, we have a really good spot about 50 meter. But after a few cycles, so one cycle in one layer with laser, it's about 45 seconds, and plus the recoater that puts a new thin powder bed, which is 50 seconds. Donc, one cycle is about 1 minute. And after a few cycles, we can reach as stable state. We can see that the starting point and the end point of the spot size is the same. And we say that the machine is hot and stable. But even it's in stable state, we can see that as function we are in the start of the layer or end of the layer, we didn't have the same spot laser. We have, at the beginning, we have 100 micrometer. And at the end, it's about 200 micrometers. So it's quite different, and you have to deal with during your fabrication. So why we have this kind of phenomena? It's because something in the optical path, so as I said before, with collimator, F-theta lens, Windows protection, there are one element actually, currently we don't know what is really big problem, but we have a deformation of one of the elements, and it's created a kind of aberration, and it creates a focal shift. So during the fabrication, we have our focal point that is I-7, as I said before, at the beginning, really beginning, and at the end it's about 0. Yes, it's about 0 millimeters. So during your fabrication, your focal points go up, and of course, it modifies considerably your spot size and your energy repartition during your fabrication. So, for example, if we work at 150 watts, you have a devolution of 6 millimeters of your focal point, and if we put more energy, so more energy will be absorbed, and we will have, in this case, 9 millimeters of focal shift. And of course, it changes the weight of the laser, so the spot size of the focal point, and of course, we have also a spread of the waist. So about 30 millimeter at 150 watts and 60 at 200 watts. It means that during a construction, for example, we start the construction we build at -3. It's an example. So we start with this energy density with a big spot. And after a few cycles, you have here with a really good spot size with a Gaussian and about 17 micrometer. This is good for LPBF. But at the end of the layer, you have this kind of laser beam, about 100 millimeter, and more spread and with energy repartition completely different. And you have to know that during the construction, we will have a balance between these two laser spots. So if it will be a problematic if you want to create really big parts where the evolution will appear. So now I will show you the results of the single tracks. You have to notice that I built this single track before the laser analysis. So at this, when I choose the parameter, I don't have the information about even the focal point of my laser. The focal points I made at -7. I find it by experiment and by my eyes. I don't know. So this is the melting pool. So we can see that in some case it's really deep inside the material. Here we go about with 800 micrometer in deep, and on the contrary, sometimes we just are on the material with no melting parameter. So I measure the depth and the width of my melting pool. This is the result. And if we want to know if we are in the keyhole regime or not, there is a criteria, which is that the depth will be more half than the the melt pool depth will be half superior of the wide. So in this criteria, we have 6 samples in the keyhole regime and 3 samples not in the keyhole regime. And now I will try to understand and to notice what is the influence of parameter on the height, the width, and the depth of the melt pool. So here, this is the influence of power, scanning speed, and focal on the height of the melting pool. So for this point, for example, I made all the sample with level 1 of focal descent, which is -5, and I made the mean. And for example, and the same for this, or all my sample, I'm -7 millimeter of focal, and here -8 of millimeter focal. And I try to make the difference between the higher value and the lower value, and I obtain for the focal distance the value of this one. I made the same for power and scanning speed. And after make a ratio, I found that the focal have a really big influence on the height of my melting pool. It's about 18%. So it's almost just the focal that changes the height of the melting pool. I made the same for wide and for depth. And we found that for wide, it's more the scanning speed that influence a lot the melt pool dimension, the wide. And for the depth, it's more the focal that influence a lot. So now I will show you some pictures. So to understand the condition of the machine when it say I try in cold and hot condition. So here we can see two pictures in cold condition at -7 millimeter focal and -8. And this is a sample at hot effect and -3 millimeters of focal. So we can see that with almost the same power and scanning speed, with just the machine condition and the focal difference, we can have almost the same aspects in my melting pool. It means that for my future experiments, I need to take in account the condition of the machine and of the optical way in my experiments. So that's it. Will I do? Sorry. For sample, I will make some sample fabrication next week, and I will build some sample with hot condition in cold condition and to compare the results. I will also continue to analyze the laser of the Pro X200 because it's really interesting, and for this moment I didn't see many publications who take into account the laser properties inside the results. And so I create sample with hot condition in order to create process windows, as I show you before with scanning speed and powder. But in more, I will addition focal distance and condition of the machine, which is really important if you want to create insert parts. And I will study so the dimension of the melting pool with electrical etching. But also, it will be interesting to study the porosity, keyhole porosity formation inside the single tract by do some tomography. And it will be interesting also to study the microstructure in EBSD to see the evolution of the grain size and the orientation of the grain with the laser sources. And after, it will be interesting to build some surface with one layer, but few single tract, in order to build after in a multi-layer and to build a 2D part with keyhole condition. Thank you.